implicit differentiation, and derivatives of rational powers. Example. Suppose that x and y satisfy the equation x squared minus xy plus y squared equals 1, whose graph is an ellipse. Our goal is to describe the slope of the curve at each point xy. Just as in the case where y is a function of x, we can define dy dx to be the slope of the graph at a point xy. To find dy dx, we proceed as follows. First, we differentiate each side of the equation with respect to x. We differentiate the left side of the equation term by term. The derivative of the right side, of course, is 0. Now, the derivative of x squared with respect to x is simply 2x. To take the derivative with respect to x of x times y, we have to use the product rule. The derivative of x is 1. We multiply that times y, and then add x times the derivative of y with respect to x. The derivative with respect to x of y squared by the chain rule is 2y times dy dx. So now let's simplify the left-hand side. We'll gather together the dy dx terms and factor dy dx from those two terms and obtain 2x minus y plus 2y minus x times dy dx equals 0. Next, we'll solve our equation for dy dx. We'll subtract 2x from both sides and add y to both sides, and then divide by 2y minus x to obtain dy dx equals y minus 2x divided by 2y minus x. This is the process known as implicit differentiation. First step is to differentiate each side of the equation with respect to x, and then simply solve for dy dx. Let's continue looking at the same example. The equation x squared minus xy plus y squared equals 1, whose graph is the ellipse that you see here. And we've just calculated that at every point on that ellipse, dy dx is equal to y minus 2x over 2y minus x. Now let's suppose that we want to find the points on the ellipse where the tangent line is either horizontal or vertical. Here are the 2 points where the tangent line is horizontal, and here are the 2 points where the tangent line is vertical. The tangent line will be horizontal when dy dx is equal to 0. That happens when the numerator is equal to 0, or where y minus 2x equals 0, that is, y equals 2x. The graph of y equals 2x is a line that goes through the 2 points where the tangent line is horizontal. Now, to find those 2 points, we go back to our original equation for the ellipse, replace y with 2x, and then solve for x. The left-hand side simplifies to 3x squared, so we have 3x squared equals 1, which tells us that the x coordinates of the 2 points are plus and minus 1 over the square root of 3. Now, since y is equal to 2x, we now have dy dx equals 0 at the points plus and minus 1 over root 3, comma, plus or minus 2 over root 3. To find the points where the tangent line is vertical, we'd like to know where dy dx is undefined. This happens when its denominator is 0, which happens when x is equal to 2y. Now again, the graph of that equation is a line that passes through the 2 points where the tangent line is vertical. So again, we go back to the original equation for the ellipse and substitute 2y for x, and then solve for y. We get 3y squared equals 1, whose solutions are y equals plus or minus 1 over root 3. And since x is equal to 2y, we conclude that dy dx is undefined, and therefore the graph has a vertical tangent line at the points plus and minus 2 over root 3, comma, plus or minus 1 over root 3. Example. Let's find the slope of the graph of the equation x cubed y squared equals xy cubed plus 6 at the point 2, 1. Here's the graph of that equation, and let's highlight the point 2, 1 as well as the tangent line to the graph there. Notice that the slope of that tangent line appears to be about -1. Now let's see if we can find out exactly what it is. We'll differentiate each side of our equation with respect to x. On the left-hand side, we need to use the product rule. We first differentiate x cubed to get 3x squared and multiply that by the other factor, y squared, and then add x cubed times the derivative of y squared with respect to x, which is 2y times dy dx by the chain rule. Similarly, on the right-hand side, we use the product rule. The derivative of x is 1, so we multiply that by y cubed, and then add x times the derivative of y cubed with respect to x, which is 3y squared, times dy dx. So now we want to rearrange so that we can isolate dy dx. On the left-hand side, the dy dx term is 2x cubed y dy dx. We subtract 3xy squared times dy dx from both sides of the equation. On the right-hand side, we have a y cubed term, and then we subtract 3x squared y squared from both sides. Now we factor the left-hand side, and we may as well factor the right-hand side as well. Now we divide by the coefficient of dy dx to obtain the fraction that you see here. Now we want to know the slope at the point 2, 1, so we evaluate dy dx at 2, 1, and the result is -11/10. Radicals and fractional powers. Let n be a non-zero integer. We want first to find dy dx if y is equal to x to the 1 over n power. If n is positive, this is just the nth root of x, while if n is negative, it's 1 over the nth root of x, where m is the absolute value of n. So we first write y equals x to the 1 over n. We'll raise each side of the equation to the nth power to obtain y to the n equals x. Now we take the derivative of each side of the equation with respect to x. On the left-hand side, we get n times y to the n minus 1 times dy dx by the chain rule. The derivative of x with respect to x is simply 1. So we have dy dx equal to 1 over n times 1 over y to the n minus 1 power, or 1 over n times y to the 1 minus n power. Now, since y is x to the 1 over n, we have 1 over n times x to the 1 over n raised to the 1 minus n power. Now, multiplying exponents, we have 1 over n times x to the 1 over n power. The exponent here is simply 1 over n minus n over n, or 1 over n minus 1. So dy dx is 1 over n times x to the 1 over n minus 1 power. Now notice this is exactly the same operation as the familiar power rule. Multiply by the exponent and then subtract 1 from the exponent. Examples. The derivative with respect to x of x to the 1/2 power, or the square root of x, is 1/2 x to the 1/2 minus 1 power, or x to the minus 1/2 power, which is the same as our familiar formula 1 over 2 times the square root of x. The derivative with respect to x of x to the 1/3 power is 1/3 times x to the 1/3 minus 1 power, or minus 2/3 power. This is the same as 1 over 3 times x to the 2/3 power. The derivative with respect to x of x to the minus 1/2 power is minus 1/2 x to the minus 1/2 minus 1, or minus 3/2 power. This is equal to minus 1 over 2 times x to the 3/2 power. Now let m and n be non-zero integers. We want to find dy dx if y is equal to x to the m over n power. So let's write y equals x to the m over n power, and notice that x to the m over n power can be written as x to the 1 over n raised to the mth power. Now we'll differentiate this using the chain rule. Since m is an integer, we know that we can apply the power rule to take the derivative of the outside function here and write m times x to the 1 over n to the m minus 1 power. Next, we multiply by the derivative of the inside, which we've just determined is 1 over n times x to the 1 over n minus 1 power. Now, the right-hand side is equal to m over n times x to a power, and that power will be m minus 1 over n plus 1 over n minus 1. And simplifying that exponent, we obtain m over n times x to the m over n minus 1 power. So again, we have the same operation as the familiar power rule. So we now have a very general power rule. For any rational exponent p, the derivative with respect to x of x to the pth power is equal to p times x to the p minus 1. So for example, the derivative with respect to x of x to the 2/3 power is 2/3 times x to the 2/3 minus 1, or minus 1/3 power, or 2 divided by 3 times the cube root of x. The derivative with respect to x of x to the minus 2/3 power is minus 2/3 times x to the minus 2/3 minus 1, or minus 5/3 power. And we could write this as minus 2 divided by 3 times x to the 5/3 power. Example: find dy dx if 2x to the 5/2 power plus 7 times y to the 2/7 power equals 9xy, and compute the slope of the graph at the point 1, 1. Here's the graph of that equation and the tangent line at the indicated point. To find dy dx, we'll differentiate each side of the equation. On the left side, the derivative of the first term, using the power rule, is 5 times x to the 3/2 power. And the derivative of the second term is 2 times y to the minus 5/7 power times dy dx. On the right-hand side, we need to use the product rule. We have 9 times the derivative of x with respect to x, which is 1, times y, plus x times the derivative of y with respect to x. Now we want to gather all the dy dx terms together on the left side of the equation. We already have 2y to the minus 5/7 times dy dx, and now we subtract 9x times dy dx from both sides of the equation. On the right-hand side, we have 9y, and we subtract 5x to the 3/2 from both sides. Now we factor the left-hand side, and then divide by the factor that multiplies dy dx to obtain the expression you see here. Now we simplify the expression by multiplying top and bottom by y to the 5/7 in order to get rid of negative exponents, and this is the result. Now we want the value of this at the point 1, 1. So we evaluate dy dx when x is 1 and y is 1, and we obtain 9 minus 5 over 2 minus 9, or minus 4/7. Another example. Find and simplify f prime of t if f of t is t divided by t squared plus 1 to the 1/3 power. We'll use the quotient rule here. F prime of t will be a quotient whose denominator is t squared plus 1 to the 2/3 power, and the numerator will be the derivative of the top, which is 1, times the denominator, t squared plus 1 to the 1/3, minus the numerator t times the derivative of the denominator, which is 1/3, t squared plus 1 to the minus 2/3 power using the power rule, and the chain rule tells us to multiply by the derivative of the inside, which is 2t. Now, because of the 1/3 times t squared plus 1 to the minus 2/3 in the second term in the numerator, we'll multiply the numerator and denominator by 3 times t squared plus 1 to the 2/3 power. Now, distributing that through the two terms in the numerator gives us a numerator in which the first term is 3 times t squared plus 1, and the second term is simply minus 2t squared. Now, the product of our denominators is 3 times t squared plus 1 to the 4/3 power. And simplifying the numerator, we now obtain t squared plus 3 divided by 3 times t squared plus 1 to the 4/3 power. Another example. Find and simplify g prime of r. G of r is r to the 2/3 power times 1 minus r to the 1/3 power. To compute this derivative, we'll first use the product rule. We take the derivative of r to the 2/3 power, which gives us 2/3 r to the minus 1/3 power, and multiply by 1 minus r to the 1/3 power, and then add r to the 2/3 times the derivative of 1 minus r to the 1/3, which is 1/3 of 1 minus r to the minus 2/3 power, times the derivative of the inside function 1 minus r, which is minus 1. Now let's factor out a 1/3, and then, to simplify further, we'll multiply this by r to the 1/3 times 1 minus r to the 2/3 divided by itself. Now we distribute the numerator of that fraction through the two terms in the parentheses. Multiplying by the first term gives us 2r to the 0 power times 1 minus r to the first power. Multiplying by the second term gives us minus r to the first power times 1 minus r to the 0 power. And our denominator is 3 times r to the 1/3 times 1 minus r to the 2/3. And finally, we simplify the numerator, and the final result is 2 minus 3r over 3r to the 1/3 times 1 minus r to the 2/3.